All right, over we go to Soton Creek. This is in southeast Washington, and I just want to acknowledge the funding sources for this and the collaboration, especially the Snake River Salmon Recovery Board. I've been working with them for over 10 years, and they've been extraordinarily supportive of the project. So just briefly, what kind of IMW is the Soton? We'll talk about then a little bit about the design and the restoration method. It's building off of the lessons we've learned in Bridge Creek and the style of restoration. And then I'm just going to hit some of the highlights for what we've done and what challenges we're having. So the takeaway here is that we've implemented the whole project. We're in the post-restoration phase, so we finished our last implementation in 2016. About 39% of the study area has been treated. Again, it's this process-based, low-tech, kind of scalable restoration that we're trying to test at the same time as figure out whether it's effective. And we are seeing positive habitat and fish trends, but it's complicated for a variety of reasons. One of the good things about this project, though, is we could have just treated one stream. We decided to treat three, and I'll show you why in a minute. And that will give us some contrast so that we can look at the different responses in different stream types. So it'll make it easier to expand these results to a variety of streams. All right, so what kind is it? It's basically the opposite of hard engineering. I was really happy to hear the Lower Columbia restoration guys talk this morning, and setting the stage of, well, there's places where you're very constrained about what you can do, and then there's places where you're unconstrained. And when you're unconstrained, you should let the river figure out how to do the restoration for you, and that's essentially what we're trying to do. Hand-built structures, high density, we're basically simulating a tree, and we're deferring the decisions to the river as much as we can. And of course, our group loves to name things. So we're calling this process-based low-tech or PBR-Lite. Again, why are we focused on this stuff so much? Well, there's more small streams than there are big streams, and there's been this tendency in the restoration community to try and apply big river restoration techniques to small rivers, and I don't think it works, and it's also just too expensive. We've got tens of thousands of kilometers to fix. We can't spend $1 million a mile and get anywhere near where we need to get to. All right, so this is a Soton. I'm very lucky. It's a good place to do an IMW. The colored watersheds there are the three streams that we're studying. Washington Fish and Wildlife has a fish-in, fish-out program that's very successful and efficient. At the bottom of the watershed, and then we have pit tag antennas at the mouths of all these streams, so we can enumerate production at the sub-watershed level, and then they're enumerating it at the watershed level. We're above 8 main stem dams, 4 on the Columbia, 4 on the Snake. We're flowing into the Snake River just above Clarkson, Washington. It's a wild steelhead refuge, so they're removing all hatchery fish. It's less than 1% sort of get to spawn on average of hatchery fish, that is. And also it's publicly owned, so this is pretty unconstrained here. I've had the freedom to try these new restoration methods, which is pretty good. This is what it looks like at the forks where they sort of all come together, Charlie Creek, the North Fork, and the South Fork of the Soton Creek. It's a hot, dry place, 10 to 20 inches of rain. But there is a contrast between these three streams, which at some point we'll get into more detail, but not today. What's the limiting factor? Well, it's the same thing that many people have talked about already. We've just got these simplified streams. They're really good at just transporting everything out to the Snake River, wood, sediment, litter, you name it. And the riparian area is recovering, but it's not putting in wood of sufficient size, so it would take decades and decades for this to recover by itself. And then, of course, there's a background climate or weather to the project, and so unfortunately, for the pre-restoration, we had basically almost double the peak flows that we were having after restoration. And then the reverse, it was cooler because there were higher flows, and so now we have warmer temperatures and lower flows after restoration. And these peaks, we've only had one fairly decent flow, and that's when we saw some of the greatest habitat change. So there's nothing we can do about that. That's just the way the cookie crumbles. Okay, so what are we doing restoration or design? So what's different about our approach? Everybody keeps saying the word balky. We're doing a staircase design, and we're doing it very deliberately. A staircase design essentially means you implement restoration over multiple years. Instead of balky, if you could, you would do your restoration all at one time. We have a statistical model to test this kind of data, and a staircase design is also logistically more feasible because you don't have to get all the money to do your restoration in 1 year. You can split it up. And then we treated all three streams, and we did that because we did an extensive power analysis and simulation of using real data to sort of look at the power of different designs. And we got the help of a statistician at Simon Fraser University. And so there's 4 designs that we looked at, 2 balky designs and 2 staircase designs. And this is the design we're doing, and these are the other designs. So this is the reason we picked this design. It has a greater likelihood of detecting an effect, more power under high variance conditions. And anybody who's collected a lot of long-term data knows you're stuck with high variance conditions. So that's why we chose this. And also, as I mentioned earlier, you get the benefit by treating all 3 streams of learning about the effect of restoration in different stream types. So that lets you expand your results to a broader set of areas. We're doing intensive monitoring, no kidding, and a lot of what I'm going to talk about is looking at CHAMP, so Columbia Habitat Monitoring Protocol, is specifically these digital elevation models. People have been doing that for a long time, but they did it at one reach at a time. We've looked at all of our sites, so we've got like 120 digital elevation models now, and are able to run all sorts of models on that base digital elevation model, and that's a little different than other IMWs. We are counting fish as well, and here's all the things we're doing for fish. Many of those look very familiar, but today I'm just going to show you some of these digital elevation model outputs, just because that's something other people don't have, or maybe not as much of. I threw this, it's awfully messy, but my point here is that I guess you could call this both a challenge and some progress. So these are habitat things that we're looking at, and these are fish things we're looking at. And my point was that, you know, we've got these different scales. If you remember back, I went through it pretty quickly, but within these large fish sites, they're 500 meters long. We have habitat sampling, so we have pretty large sites. We did that for a specific reason too. And then these are the data that we've collected. So this is sort of in hand, you know, we have the full range of survival estimates, but this is what we've analyzed to date. So that, you know, I've admitted many times it's great to have all this data, but it takes an army to go through it all and to maintain these databases, and that's a challenge, and it costs money. You can't sit down in an afternoon and just whip out an Excel spreadsheet on any of this stuff. It takes days and weeks and months of maintaining data, cleaning data, and then trying to figure out what analysis to do and produce it. So just want to throw that out there. Okay, our restoration, it's simulating a tree. So we think of the method as high density. We're going to put a whole bunch of small trees out there, and we're using methods similar to Bridge Creek, where we use a post pounder to sort of tack some of the wood in place. And we build different types of structures. These are all common structures that have been built forever. So we've treated 14 kilometers out of 36 kilometers, built about 700 structures. So they're pretty densely packed together there. They're hand built. We can build 10 to 20 of these a day. We don't have any fancy engineering diagrams. We just are trying to simulate trees and falling in the river, and then if some of this wood moves, we're not too worried about it. Okay, moving into sort of results and challenges. People were really concerned when we first proposed this method that all this wood was going to blow out, and so we do go to every structure, so 700 structures every year for the first 5 years, and record how they're doing. And this is just a scale basically from they're gone to, oh, there's some new ones that we didn't even build these. And so the takeaway from this is, yeah, we're losing some, but we're building almost as many. And then we have this range of structures in between. So, they're mostly staying there. And this, like I said, this is after 5 years. And this is another thing we got grief on, but I think I've convinced people this makes sense. We're maintaining our structures when needed. So every year we go look at the structures. If we think the wood density is going down, we're going to put some more wood in there. And we can do it really cheaply now because we have basically this Velcro in all of these treatment areas with structures everywhere. And so we can just use grip hoists or chainsaws and drop some trees in or drag some trees in and just let that wood now get caught wherever it's going to get caught. We've spent $10,000 in the last 3 years just maintaining structures. So it's really low cost, simple to do. A couple of people can kind of do this. Just quickly, sort of habitat responses. This is looking at one individual structure, and so this brown line is the structure. This is upstream of the structure and downstream of the structure. And then how is the habitat changing over time? And we've got 700 of these times 5. This is a good example, and so we see habitat change out there. That's great. We see it with our eyeballs. We do rapid habitat surveys. One thing we're seeing a lot of, and I heard lots of people mentioning this too, like sediment to me has become the new sort of habitat that I'm interested in. I think it was very underappreciated in the last 20, 30 years of fisheries habitat work, but sediment is everything about rivers. And so we're seeing huge bar deposits. It tells us that these structures are trapping sediment, sorting sediment, and building up the bed, which in itself can help create complexity and pools. The rapid habitat surveys, show us that, yeah, we've got more wood in there than we used to, and we've got more pools. That's great. What I was really interested in, though, and now I'm diving into these digital elevation models, we basically have algorithms and programs that can go into a digital elevation model. So this is topography, just plain old topography, and it can find these different features because they have a topographic signature. And so we call that GUT, the geomorphic unit tool. That was developed at Utah State. You can run this on dozens of sites at a time. So we've run this now on all 100 sites, or sorry, we've run it on, we have 18 sites, but we keep going back. So we have 120 or so of these maps of geomorphic units. These are tier 2, so just looking at, is it a pool, is it a bar, or is it a planar feature? But we can also dive into, well, what kind of pool is it, what kind of bar? So that's tier 3, and that's what this map is. And I've got the data that goes with this, so I know the area of all of these units now in this particular reach. And I was hoping to show you a slide that went, look, we've got way more of this and way more of that, because when we cherry pick and look at some of our good sites, we see it. But when I look at the whole treatment versus control, I'm not seeing those patterns. I'm not sure why, because we see it on the ground with these rapid surveys. So we've got some work to do to figure out what's going on there. There's definitely change, but like some other IMWs have found, it's not significant when you look at it at this scale. Maybe we're looking at it too fine a scale. I'm not sure. I'm going to switch now and just look at some fish. So first positive trend, similar to the Bridge Creek thing, we've looked at the treatment minus control, and then these dots are just showing the actual effect response of fish abundance for the 3 different streams. So they're all positive, but 2 of them are, the confidence intervals are crossing 0, so they're not significant, but everything's sort of trending in the right way. So the North Fork is a larger stream. Habitat change is a little easier there because it's more of a wandering gravel bed stream. These other guys are pretty confined, higher gradient. That may have something to do with it. And so the first question I'm asking myself, and now I finally have some data to look at, is, well, if we're getting more fish, in theory, we have a higher survival somewhere. So this is just a summary of the North Fork age 1. We're assuming those younger fish maybe are going to respond more to the restoration. And so we see that we have this lower survival in the winter compared to the summer and the fall. There's no spring here because when they migrate, they transform from age 1 to age 2 is the way we're collecting the data. So we just have 3 seasons. And so if we look at, now I'm looking at a geo mean of survival in the winter, expecting to see, here's the control before, here's the control after. So survival's gone down a little bit, and then here's the treatment before and the treatment after. That's a, you know, a tiny little bump that's probably not even anywhere near significant. So that was a bit of a surprise. But if I look at fall, we see this huge change, again, for age 1 fish. So this is just sort of early stuff. We're trying to figure out, okay, we see an abundance effect. What's causing it? Now, the other thing we've put a ton of effort into is this net rate of energy intake. I'm going to go through this really quickly, but again, these are all CHAMP inputs. So we got a digital elevation model. We collect food, temperature, and then some characteristics about the fish. And we use that to come up with a map of basically what's the energy cost at each one of these dots. And then if you use fish territory rules and exclude, you drop a fish point wherever is the highest energy intake, and you keep doing that till you fill up your whole reach, you can actually get some estimate of carrying capacity. And we also included in these models the actual structures. We digitized them in and we gave them some kind of porosity. And this is a paper we've published, a couple papers we've published on this. You'd expect, this is a distribution, is the dark bars of these NREI values before restoration, and you would expect there to be a shift to more positive, better places for fish to feed and grow after restoration. And if we look at, again, the same graph, so here's control before and after restoration, so we see a decrease for some reason here, and we get a little bump in the treatment area, and this is for the North Fork. And if we look at the South Fork, we're seeing the same trend, and Charlie, the same trend. Control is either not increasing or decreasing, and the treatment is. So this gives us some indication that we're actually creating better sites for fish. It's a modeling approach. We're also going to count all the smolts going out and do all the other metrics that other people are doing. We've done that up to 2016, and hopefully by the end of this year, we'll update that to 2017 or 2018. And yeah, look at that, 33 seconds. Whew. So takeaway, yep, we're in a good place right now in the Asotin. We've got everything implemented. We're kind of on schedule. The ugly stuff now is just interpreting and managing this data. And I think there's a tendency for people to think that this data is going to just miraculously give you an answer. And I think we're underestimating the amount of time it's going to take to look for trends in your data, and then try to understand why you do or don't see things that you're predicting. And that's where we are right now. But I think this is again, like Bridge Creek, it's a low-tech, widely applicable restoration method, and looking forward to sort of figuring out how effective it is.